Hey guys, welcome back to another RSK Maths tutorial, and in this tutorial I'm going to be showing you guys how to integrate polar functions. So just a reminder, polar functions are functions where we have a function r of theta, sometimes just written as r, and it's just obviously some function theta. So it could be sine of theta, cos of theta, anything related to theta, or it could just be 1, and to plot them we use a sort of different sort of plane, and we care about the radius and the angle it makes. So if r of theta equals to 1, that means the radius is always going to be 1, no matter what angle it is. So I know this is a bad circle, but this is a circle with radius 1. So the question we're asking is how we're going to integrate this, or in a different sort of question, it's how we're going to find the area between two given intervals of theta. So if we were trying to do between theta equals 0 and theta equals 2 pi, theta equals pi over 2 or 90 degrees, then we're trying to calculate this area here. And what this comes down to is finding a formula for the sort of base unit of the integral. Like on a Cartesian plane, if we have a function here and we're trying to integrate it between these two bounds, what we do is we split this area into a bunch of tiny rectangles like so, where each rectangle has a height of y and a width of dx. Then when you sum them all together, you get the total area is going to be the integral from bound 1 to bound 2 of y dx, where y is a function of x. So we could just write this as f of x dx, like so. So that's what we think about when we're integrating on the Cartesian plane. Now on the polar plane, it's similar, but all we do is, instead of using rectangles, we're going to use really small triangles. And you can imagine if we have a bunch of these really small triangles, as they get smaller and smaller, it's going to eventually just become the same as it's going to become the same as the original curve. So if I draw loads of little triangles like so, eventually all of these errors over here, as they get really small, it's just going to disappear. And let's look at an individual triangle. So let me bring this over to here. Okay. So an individual triangle, this is going to have an angle theta, and each of these lengths is going to be of length r. We're assuming as this gets really small, then this r is going to be the same, since this theta is going to be tiny, so the amount of that r has changed is also going to be tiny. And we don't worry about this length for now, because we know that the area of this triangle can be calculated using the sine formula, or 1/2 r squared sine theta. Okay, now remember, let's actually call this angle d theta, just because we want to represent that it's going to be really tiny. So this becomes sine of d theta. So that would imply that to calculate this area, we take the integral from 0 to pi over 2 of 1/2 r squared sine of d theta. Now, it seems a bit hard to integrate something with sine of d theta in it, right? But what we need to remember is that this becomes exact as d theta approaches 0. So as d theta approaches 0, sine of d theta just approaches d theta. And this is related to the approximation sine x approaches x as x approaches 0, just because in the Taylor series of sine x, it actually expands to have a x term and then other terms, but since those are all powers of x, they start to go really small, and it just becomes similar to the x term. So that's all we have to remember. As d theta goes to 0, which is what we're looking at, which is what we're considering, this actually just approaches d theta. So overall, the area of any polar equation, can be figured out using this formula, the integral 1/2 r squared d theta between the two bounds. I've just picked 0 and pi over 2, but this could be anything. So let's actually use this to work out what this area is going to be. And remember, this area is actually a quarter of a circle, which the circle is radius 1. So we know the area has to be equal to pi r squared over 4. And we know r is just 1, so this is just going to be equal to pi over 4. But now let's try and work out the area using the integral. So we're integrating from 0 pi over 2 of 1/2 times r squared, which is just 1 squared d theta. And from here, since this is a definite integral, d theta, we can just replace this with an x and replace all the features with x's. There aren't any. Let's move that 2 outside. That 1 just does nothing. So this is ultimately the same as that, which integrates to this. And then we get 1/2 times pi over 2 minus 1/2 times 0. So you can see that that simplifies all the way down to the area equals pi over 4. Just like that. So there's our formula. Pretty simple. We've managed to derive it. And let me write it out in full. To integrate a polar function between bounds a and b, we get the area is equal to 1/2 times the integral from bound a to bound b of r squared. Sorry, let me just write r of theta squared d theta, like so. Okay, so there's the answer. Thanks for watching, and remember to use this formula to integrate polar functions. See you guys in a future tutorial. Bye.